I'm going to be kind of introducing this topic and talking about how transfer functions can determine the stability of the control system. So the roots of the denominator of the transfer function are what determine the stability and behavior of the control system. So you can kind of have three main behaviors for a control system where it's stable, where the output response is bounded for all bounded inputs, which you can see on the left-hand side where we have our function y of t. And as a function of time, you can see as time goes to infinity, we're reaching a stable value. An unstable system would be one where the function is going to infinity as time goes on and we aren't kind of reaching that single value. Additionally, we can have oscillatory systems which kind of just fluctuate between different values, and these systems can then go on to infinity or they can eventually stabilize to a single value. And so going into transfer functions and how these determine what our process response is going to be, I kind of have two main general examples to show. On the left-hand side over here, you can see that we have real roots. And so this is a transfer function that has real roots. And so this transfer function is g of s equals 1 over s minus a. And the characteristic equation of a transfer function is this denominator. So here our characteristic equation is s minus a is equal to 0. So setting that denominator equal to 0. And our roots of our system are where the denominator equals 0. So in this case, that's s is equal to a. And if you take the inverse Laplace of your original transfer function, you get the function of the system. So for this example, that would be y of t equals e to the at. And then going into complex roots is the same process, but just for a different transfer function that leads to roots that are complex. So here our transfer function g of s is equal to 1 over the quantity a minus s squared plus 1. And so you can see the characteristic equation is just setting that value equal to 0. The roots we can see are complex, where s is equal to a plus or minus our imaginary number I. And then again, taking the Laplace of that original function, we can see that we get y of t equals e to the at times sine of t. So these are two general examples, and we'll be able to see for these different roots what process response these give us. So now going into kind of what we can expect from these roots, you can see I kind of have a summary at the top where the real roots are on the left side and the complex roots are on the right side. And first, getting into the real roots, we know that our root is where s is equal to a. So now going down here, if our root is negative, if a is less than 0 down here, then you can see that this function, y of t equals e to the at, it's going to be e to a negative t value. And so that is eventually going to stabilize as the system goes on. So bottom line is that if you have a negative real root, then your system is going to be stable. And then similarly, if you have a positive real root, so in this case for this function, since our root is a, if a is greater than 0, you can see that the system will go to infinity and you will have an unstable system. So now getting into complex roots, you can see the function here again. Here we have roots that have both an imaginary part and a real part. So we know that a here represents our real part. And so here, if a is negative, if it's less than 0, then you're still going to have an oscillating system because of that complex root, but it is eventually going to stabilize to a single value. For complex roots that have a positive real part, then your system is going to be unstable. So here we can see that a is greater than 0, and again, a is our real part of our complex root. And so you can see, looking at the function, that it's still going to oscillate because of our sine term, but it is going to be unstable because that e to the at term is not going to stabilize the system. And so this is just a general example of how you can use transfer functions to be able to determine the behavior of your system. And so the bottom line to remember is just that negative real roots And complex roots with negative real parts are what lead to stable systems. Because one way to go about finding the behavior of your system. There are other ways, which we will talk about later in this video.
So another way to assess dynamic behavior is through the Routh stability criterion. The Routh stability criterion was developed in 1905 by Ralph Horowitz. Given a characteristic equation where an is greater than 0, the Routh criterion states that if any of the coefficients a naught through an are negative or 0, then at least one root of the characteristic equation lies in the right-hand plane, where on this figure you can see the right-hand plane in this case indicates the unstable region. So this allows us to determine behavior. Now, if this isn't the case, and if all of the coefficients of the characteristic equation are positive, then you have to do a little bit more digging to determine the behavior. You have to construct a Routh array, which is what you see here. So using the Routh array, we would want to examine this first column. And if all of the coefficients are positive within this first column, then it means the system is stable. And you can see these first two rows are just coefficients from the characteristic equation. And then these next two rows, 3 and 4, we need to start using these equations that I have listed off to the side here. So I think the best way to learn this is going to be putting it into practice. So I have an example problem here. So in this case, we're looking at a feedback control system, and we have the block diagram for it below. We want to determine the values of Kc that result in a stable closed loop system. So what that really means is what values of Kc will make that first column of this table positive. So I've already gone ahead and found the characteristic equation by identifying these nodes here, finding expressions for these nodes, and solving a systems of equations to find this transfer function. And as we know, the denominator of the transfer function is the characteristic equation. So that's what we're going to be analyzing to determine the behavior. So looking at this characteristic equation, we can start filling in our Routh array. We see the first row, we want to find A3, that's going to be 1. We have a n minus 2, which in this case is A1, that will be 35. For A2, that's 14. And A0 is this constant here, 4Kc minus 50. These next two rows get a little bit more complicated, so I'm going to solve them off to the side. For B1, we have, you follow along, it's 14, it's 35 minus 1 times that big constant 4Kc minus 50. And this will all be over A2, which is 14. So we can simplify this down to 540 minus 4Kc over 14. So that's what goes right here. And now we're on row 4, so we're going to be solving for C1. This is also a little bit more complicated, so I will write it down here so we can simplify before we put it in our table. So that will be E1, which we just solved for, times that constant. This will end up canceling to 0. That will all be over that B1 that we just solved for. So when we simplify this, it's just that constant that we've been seeing, 4Kc minus 50. So these two values right here are already positive. Now we just need to find what values of KC will make these positive. So that will lead us to our final answer of a range of KC values. Therefore, 540 minus 4KC over 14 must be greater than 0, and 4KC minus 50 also must be greater than 0. So when we solve for the KC values that correspond to this, we find that KC must be less than 135, and it must be greater than 12.5. So this gives us our answer to the problem, all by using the Routh array. So we know that the range of KC values must be from 12.5 to 135 for the system to be stable.
All right, so I'm going to go over a few examples using the tools that have been introduced. This first one goes over some of the methods introduced earlier. And so here we have this equation that represents the process response. And so what we're going to do is analyze the denominator, and we're going to determine the roots of the denominator to predict this dynamic behavior. So using the quadratic formula, we get that these are the roots. And then further looking at that, since we have a complex root, we know that the behavior will be oscillatory, and then since it's negative, we know that it will be stable or bounded. So here is kind of a sample of what that behavior could look like. We see that there are oscillations, but it is stable and will kind of converge as t goes to infinity. The next example is going to use concepts relating to the Routh array. And so here we have our characteristic equation that we're looking at, and we look at the coefficients to then determine the behavior, and we're actually going to, like I mentioned, use the Routh array. Based on the formulas that were discussed earlier, this is what the Routh array would look like. And then, based on the rules we discussed, since there's a negative in the first column, we know that this response is not stable. Additionally, we would need to do further analysis to determine more specific behavior.